Hello guys, today we're going to be covering section 4.7, which is optimization problems. So optimization problems is kind of an extension of what we've been doing with calculus. Derivatives so far really, it's just, taking derivatives and looking for maximum minimums of functions. Specifically, optimization problems kind of occur when, when we have something we want to maximize. So maybe like, profits is always a nice thing to maximize, fuel efficiency. Nice thing to maximize, or things we want to minimize, the cost or something, or we want to minimize the surface area of something. Well, a lot of optimization problems kind of show up a lot, so in order for us to solve them in a very nice way, we can use calculus, we can use derivatives. So this is kind of the point of this section. So we have a strategy that kind of talks about, a kind of strategy that allows us to talk about solving optimization problems. And the first thing is we want to understand the problem. What's given, what's unknown, and we want to read the problem carefully. It's basically just like, okay, understand the problem fully, that way you can understand the mathematics behind it and what you need to do. The second step, usually draw a diagram. Drawing a diagram definitely helps. It allows you to identify given and required quantities, and is like always recommended if you can do it. If it the problem has something you could draw, just go for it. The third thing you want to do is introduce notation. Once you have a diagram, once you understand the problem, you will need to assign some symbols to stuff. So assign a symbol to the quantity you're trying to optimize, and symbols to the quantities it depends on. Use letters like A for area, H for height, B for volume, etc. You could, say H for volume and V for height, B for area if you really wanted, but typically you want to keep it so it kind of makes sense in terms of the problem, and that way it's just easier to get information from. You can use, any character you want. You use kanjis if you want, but it doesn't matter. You just try to make it easy for you. The next thing you want to do is, express a quantity we're trying to optimize in terms of the other symbols. So you want to define like a relationship that we want. Typically, we could say y is equal to f of x is typically 1. We have what we want in terms of something else, what we know. And typically this is a pretty standard thing, and the idea is for 4 is we need to do some math on it. So in order for us to do math, we need some relationship between the quantities. So, if there are multiple variables on one side of the equation, we find a way to rewrite the equation purely in terms of one variable. So, we want to try to write, y is, equal to f of x, not y is equal to, f of x, h. You want to try to, bring down the number of variables to minimum. That way it's easier to solve the problems. And lastly, when you find the absolute maximums, of the new function, you usually want to use, the methods from previous sections. So the closed interval method, there's going to be one thing we're going to do next that kind of shows us another way to do it. But typically, just use what you know to solve the problem. Basically what it comes down to. So finding the absolute maximum or a minimum of a function can be difficult if we can't apply the closed interval theorem. And this could be a case when we're not really working on a closed interval, when we're working from 0 to infinity or something like that. Typically time can be considered one of those kind of domains. Usually you don't work with finite time. Anytime you're working with something with time, typically can go on forever. But we do have another test that can be useful, which is the first derivative for absolute extreme values. So suppose that we have c is a critical number of a continuous function f on a closed interval. Really what we need is never mind, this is fine. It doesn't really matter if it's a closed interval or not, because the closed interval method would still apply, but typically the fact that it's a closed interval is not so important here. What's so important is going to be these few properties. So if f prime of x is greater than 0, for all numbers less than c, or f prime of x is less than 0 for all x greater than c. So in this case, the graph of that would look like that, but then you would have a maximum value at c. And likewise for b, the second part, it's basically the same kind of idea, but now it's the opposite, and you get the minimum value instead. And the thing is, it's like the closed interval method, you usually have to account for, what's happening around the function. What's typically what's happening around, you have to include the endpoints as well. But there's some nice cases where, you don't really have to do that. Because what happens is that the function's, that's just going to be its maximum everywhere. So, again, we're kind of talking about the picture looks like, if f is increasing for all x less than c, and f prime c is equal to 0, that's what it means to be a critical number, then f decreases for x greater than c. And then we get, the fact that it's like a minimum. So basically this would be like the setup for the first one is that, here we have the functions increasing, here we have the function is decreasing, and it's always going to be decreasing or increasing in those sections. And because of that, it can never go higher than fc. And that's kind of where it comes from, you're only increasing, you're only decreasing. So, we can use this to we can use this on any closed interval, so we could cut it off here and here, cut it off here and here. And basically as it comes down to, if the fact is, it's if you're working on some space and you can only, if you go up and up, if you your derivative is always positive, and then, eventually up to a certain point, and eventually it'll stop being positive, once you get to that critical number. Now, once you've reached to that height, if you don't ever increase again, if you only decrease afterwards, if you only, go back down afterwards, you will never ever get back to that height. And that's what this is basically what it's saying. It's that's the idea. So you'll never go back higher than f of c, than the maximum. And likewise for the minimum. So let's do an example, let's do something concrete. I went over these two I went over the two in the, this example, the next example during the lecture, so I'll try to keep these fast. But I'll still go through them. And I have two more examples too, which I'll go through kind of fast. So suppose you have a cylindrical can, and it's made to hold 1 liter of water. Remember, a liter is like a volume. Well, not of water, but of oil. But typically, liter is volume. Cylindrical can, you want to find the dimensions to minimize the cost of the metal, to manufacture the can. So what you want to do is minimize the dimensions. You want to minimize the surface area because the surface area is basically going to tell us how much metal we need. So you want to minimize, let's see, the metal, which is going to be, and again, it's a cylindrical can, so the metal is going to be used to be the surface area. So here's like a cylinder, it's got radius r, and it's got height h. And we know the volume of a cylinder is just going to be, the area of a circle times the height, so pi r squared times h. And we said previously, it's made to hold 1 liter, so the volume is fixed, so the volume is 1 liter. But we're going to work with as, 1,000 centimeters cubed. And our goal is going to be to minimize the surface area. So you want, the whole surface area of this can to be as small as we want. And well, as small as possible, while maintaining the fixed volume. So this is kind of where it comes to, the relationships. For 1, the first thing we did for 1 was, read the problem. Cylindrical can made to hold 1 liter of oil, find the dimensions, minimize the cost of the metal to manufacture the can. So, we kind of get the problem, there's a can, it's a cylinder, holds 1 liter, so that's a statement about its volume. We want to find dimensions that minimize the, the metal that we're using. So, minimizing the surface area. So, we're going to let, this be our volume. We set it equal to 1. So this is kind of where symbols kind of come in. We say, the radius of the can is going to be r, height of the can is going to be h. This is drawing a diagram, make it as consistent. We also want to try to write down our goals. You don't really have to do that, but it's always a good idea to do that. That way you know in your head what you need to solve for. And the next thing we have to do is, try to find a relationship. We want to find what we want to minimize So in this case, this is going to be A for surface area. So maybe SA if you want, but really we're just going to keep it A. So we want to minimize the surface area, and the first thing we have to do is set up a relationship with the area in terms of, the cylinder. So if you look at the cylinder, this will be like the top piece, this will be like the bottom piece, and this will be like, the thing that actually wraps around. So, like this, or whatever. I don't know how to draw that. So if you figure out all those areas, the area of a circle is going to be pi r squared, another pi r squared, and then this right here, this length right here will be corresponding to this. So that will be like, 2 pi r, and the height is h, so we just get, pi r squared plus 2 pi rh. So 2 pi rh. So that's how we get this. We add them together and we get the area. The surface area of a cylinder is equal to 2 pi r squared plus 2 pi rh. So, sorry, I was yawning. But, so far this is pretty good. It's not too difficult. And we just now have a relationship with, for the surface area in terms of r and in terms of h as well. And this is going to be a problem because typically when we find, derivatives, we so far have only talked about them in terms of one variable. And this is where we kind of have to use some other information that we have, is that pi r squared times h, like the volume, is equal to 1. So if you want to just write this by itself, just with math alone, this is 1 is equal to pi r squared times h. So we could easily just solve for h and then just plug it back in. So you can solve for h here and then plug it back into the area. So that's what we're going to do now. That way, whenever we plug it in, we get rid of this h and only write it in terms of r. So again, turn the area function to a single variable. Currently it depends on the radius and the height. So we know from the fixed volume, pi r squared is h. Well, pi r squared times h is equal to 1,000. I said it 1 earlier, but that was 1 liter. But here we're working with centimeters cubed. So we just get 1,000 divided by, pi r squared. I should mention we change into liters because we want to write something, we want to write a volume in terms of like 1 liter, that's going to be 1,000 centimeters cubed, and the cubed part represents, like a length times width times height, all measured in terms of, centimeters. And a radius is usually measured in terms of centimeters, so that's why we're changing it back to centimeters. So we got h is equal to 1,000 divided by pi r squared. We're going to plug this into the surface area formula, where we had, this was h. We plugged it in, simplified, we get a is equal to 2 pi r squared plus 2,000 divided by r. So that's going to be our new surface area in terms of just r. If you want to minimize this function, again, it's kind of the goal of the problem is, optimize, in this case will be minimize. And what we do here is we just take a derivative. We want to find the critical numbers because, we know the critical numbers correspond to the maximum and minimum values of a function. So we take a derivative, and eventually what we get is just, 4 times pi r cubed minus 500 divided by r squared. All I did was algebra to put it all together. The critical numbers are, again, when the derivative is undefined or equal to 0. So one of the critical numbers will be r is equal to 0, so one will be undefined. But that corresponds to no can, because like a cylinder with radius 0, that's meaningless. Like you could have an infinite number of those. Like those are nothing. It literally is nothing. So we're going to disregard that. So the only other case we have to worry about is whenever pi r cubed minus 500 is equal to 0. So we can solve for that r, and we get r is equal to the cube root of 500 divided by pi centimeters, which is roughly equal to 5.4 centimeters. So next thing we need to do is verify that it's an absolute max or an absolute minimum. So we do interval testing. We could break up the interval into 0 to square root of 350. The cube root of 500 divided by pi. I don't know what I said there. We do interval testing. We get it's decreasing and then increasing. This is all pretty standard. So A is decreasing to the left of R, so that R value, and is always increasing to the right of that R value, so it is an absolute minimum. Which itself is pretty awesome, and it's exactly what we want. So the dimensions that minimize the cost of the can are is R is equal to, the cube root of 500 divided by pi centimeters. And the height will be 100 divided by pi r squared. So we just solve for that R now, we could plug it back in. And we get 1000 divided by pi times 500 divided by pi to the 2/3. All we did was just plug in for that h. We didn't bother simplifying, it doesn't really matter. So those are the dimensions that minimize the surface area of the cylinder. So that's going to be our n. So, that example in itself wasn't too bad. It was just, trying to understand the setup. But, we're going to do through more examples as well. So in this example, we're going to have a, let me just read it. If 1200 centimeters squared of material is available to make a box with a square base and an open top. So there's no cover, there's no top of it, it's just open. And we only have those 5 sides, the bottom and the sides. And we want to find the maximum possible volume of the box. So one of the things we should notice is that when we read through the problem, we have 1200 centimeters squared of material, and we want to make a box out of it, square base, and an open top. So square base, so if we just think about a box by itself, say like, whatever, that's a horrible box, but whatever guys, I think you guys get it. Man, that really is a horrible box. Ugh, whatever, you guys will deal with it. But typically volume is, length times width times height. But what the square base is telling us is that basically 2 of those things are the same. So remember, when we draw the box, like what I did here, number 2, draw a diagram if possible. So this will be the base, will be the square right there. It's square, so both the side lengths are the same. And it'll have some height h. So what we know is that we have 1200 centimeters of material available to us to make the box with. And that availability of, the material basically means we have, 1200 centimeters squared of surface area. And we know the equation for surface area of a box, it will just be the base, so the area of the box, so b squared, plus the area of all the sides. Each of the sides is just going to be b times h, so 4bh. So b squared plus 4bh is equal to 1200. And our goal was to, maximize the possible volume. So to find the maximum possible volume of the box. So, the volume is going to be equal to b squared h. So again, the volume is in terms of 2 variables, b and h. What we want to do is, use the surface area equation, and then solve for h in terms of b. And you might ask me why are we choosing h instead of b? Well, if you look at the equation right here, h is pretty, right here is just h, right here is just h. So that in itself suggests it would be pretty easy to solve for. If you look at, b squared, like we could put in b squared right there. Or if, we try to solve for b of this equation, it would just be kind of a pain. Sometimes they're both equally valid, it doesn't really matter. It's just, choose one that's easy and just stick with it. If you did either or, and as long as you did all your math correct, you'd still get to the same answers. So we can solve for with the surface area equation, we can, solve for h. We get h is equal to 1200 minus b squared divided by 4b. So we can plug into the volume equation, and we just get v is equal to b squared times h is equal to, all that kind of stuff again. Just plug it in, reduce. We get 1/4 times 1200b minus b cubed. And, again, we want to find the critical points. Or, we want to find the derivative set equal to 0 or when it's undefined. And I wanted to kind of clarify something. This is what I did during the lecture. Again, that, what we're doing is kind of different from what we normally do. When we take functions, we take the derivatives, those are just rules. Those are more arbitrary things. But here we're working with like just one single box, and we're messing around with the parameters of that box. So what I drew here is basically that graph of 1/4 times 1200b minus b cubed. And what that is, that's like a cubic polynomial. And so we expect to have a maximum and a minimum. And, spoiler alert, I've already kind of done some of this. This is how I know the graph looks like. But one of the things you should notice is that, this is, this curve is going to be this curve right here. So what's really happening is that we want the volume in terms of like, the side length. So b is, the length of like, one of the side lengths of the square. Or, the length of the box. So the volume is going to be like a function of that. So for each base we choose, we're going to get a volume associated with that. We choose a different volume, we'll choose a different base length, we get a different volume, and so on. So this is where even though taking a derivative, what does taking a derivative of a volume mean? This is what it means is, the change in volume with respect to the change of base. But, that in itself is kind of weird. Like, why would we consider that? But you have to understand that, we're working in like a parameter space kind of way. We're considering all possible, ways we could build this box. And we're not really looking for, how the box itself is changing. What we want to know is if we increase, the width of the box, how does that change the volume? So it may seem a bit weird at first, but understand that a lot of times we will have a fixed object, even though we're talking about one box. We want to talk about all the different possible variations of the box and all the parameters of the box. So that's why, even if a derivative kind of makes a little weird, but we want to find the area, we want to find the, the b that maximizes the volume. So, we take a derivative and we find the critical numbers because we know those correspond to max and minimum. So that's what we do. So we find v prime, we set it equal to 0. To get, v prime is just 1/4 times 1200 minus 3b squared. Set it equal to 0, we should get b squared is equal to 400 eventually. We get b is equal to 20, because really you get, plus or minus 20, but we only really care about positive length, so we just drop the negative version. So next thing we need to do is show that it's a max and min. And again, this is just pretty standard interval testing. Remember that this is going to be on v prime. So we plug in, 1, which would be all the way to the left of 20. We plug in 21, which would be right here. Oops. And what we get is, it's going to be increasing from the left of 20, decreasing from the right of 20. So we get that it's a maximum. And remember that, what the derivative tells us, what this is saying is that v prime is, v prime is positive here, v prime is negative here. But what that does corresponding to the volume is that, it's decreasing, and with that terms, and whenever v prime is greater than 0, positive, that means v itself is increasing. So the volume would be increasing. And again, so we get to the volume, the largest box is just, we had what b was, b is equal to 20. We plug it into our volume equation and just plug it in. So we get, 4,000 centimeters cubed. And note that in this case, they didn't ask us for the dimensions of the box. We just wanted to find the largest possible volume. So in that case, we just had to find the volume. We just had to plug in the number and find it. In the last case, they wanted to find the dimensions, so we had to find, the r and the h. We had to find the radius and the height of the cylinder. All right, so here's another example that we did. Well, not an example, but here's a new example for you guys. So suppose we have two positive numbers such that they're products, so when we multiply them together, we get 192. And the sum of the first and 8 times the second is, and is as small as possible. I said oh crap because I thought I didn't, specify to minimize it, but the idea is we want to minimize, this is going to be like a minimization problem. So, like, kind of the first thing is, two positive numbers. So we'll say, like, A, B. Actually, let me just kind of go through it. So, two positive numbers such that their product is 192. So let A, B be our numbers. So that's just good notation. And then we know that A times B is equal to 192. And that's what that first sentence tells us. And the second part, well, not the first, but the first part tells us. But the second part tells us that we want the sum of the first, so A and A times the second. We want A plus AB, 8B, so A plus 8B. Oh, that sounds weird. We want that to be as small as possible. So we know this, and our goal is to minimize this. So what we need to do is, like, there's no equations right here. This right here doesn't have an equation in it, but it's two variables in it. And the way we can talk about this is, we'll go into an expression how we want to talk about it in just a second. So again, we kind of want to try to find a way to represent this in terms of one variable. Even though so far it's just an expression, we still want to minimize it. Our goal is to minimize it when, A and B are positive. So we can just take the fact that their product is 192, solve for A. It doesn't really matter which one we solve for. It could be A or B in this case, really. So we get A is equal to 192 divided by B. So A is equal to 8 plus B. So we get 192B plus 8B. So we're going to so that's going to be a new expression in terms of just A. So we let f of B equal to 192 divided by B plus 8B. So in this case, when our two numbers here, we, our two numbers that we chose, oh, I'm so stupid. The two numbers that we chose here, they're fixed. We want to find them. But the way we can do that is by being more general. So when we do f of B like this, we're just saying, okay, now we're going to let B vary and know that the B that we want is the minimum solution here. So when we define our function to equal our expression in terms of just B, we want to find the minimum value of f, the minimum value that, we can actually, that's obtainable, that's meaningful for us. So thus, we want to find the minimum, we want to find the critical points, we take a derivative, we get f prime of B is equal to negative 192 divided by B squared plus 8. So the critical numbers are going to be B is equal to 0, but that's really just going to be undefined. We don't want B equal to 0. We would have A times B is equal to 1, but we still, because we have the product equal to some non-zero number. So, the other thing we do is take the derivative, set it equal to 0. And eventually what we get is B is going to be equal to plus or minus the square root of 24. Again, we said B is positive. And it just simplified it, so B is equal to 2 root 6. Approximately equals to 4.8989 or whatever, or 4.9, doesn't matter. And now what we want to do is determine if, f of 2 root 6, that B value that we got really is it really is a minimum for that function. So what we can do is just do interval testing, and with the function with f prime, f prime is equal to negative 192 divided by B squared plus 8. So we plug in different intervals for the function. So we get f prime of 1 will give us a negative number, f prime of 8 will give us a positive number. So that tells us that's a minimum. So it's going to look like this. Well, specifically an absolute minimum. So, oops, I think I forgot to write it. So B is equal to 2 root 6 is a minimum. Well, I'll say f of that is a minimum. And lastly, remember that we wanted was, we wanted to find the numbers A and B. So remember that, A was equal to 192 divided by B, but that's going to be equal to 192 divided by 2 root 6. So that'll just be equal to I think 96 divided by the square root of 6. Yeah, I think that's right. So our a will equal to 96 divided by the square root of 6. And our b is equal to 2 root 6. So when we multiply them together, we get the smallest possible value for, 8 plus 8b. And when we wrote that in terms of b, that was just like, 192b plus 8b. So it's not too bad. This one's a bit more abstract, but it's like a kind of number theoretical problem, and it's pretty nice. It is a bit more abstract, but again, that's not too much of an issue. You just have to make sure to understand that, when you get this expression, you want to minimize that. You want to write it as a function. So really, you would write this as like f of a, b, and the goal is you want to find the a's and you want to find the a, b's that minimize that. Now for the last example, this one I'm going to be kind of doing with you guys, sort of, but it's going to be a bit more complex. So suppose we are the manager of an apartment complex with 50 units. So we have an apartment complex, we just have some building, and we know that's got 50 buildings, so 5 floors, I don't care, so 50 units. And what you know is that when we rent out, we set rent to be $800 a month, all the units are rented. So basically that tells us, we're like, okay, our price is low, everyone's going to be able to afford it, so it's filled. And we have that as you increase rent by $25 a month, one fewer unit is rented. So every time we increase the price by by 25, we get one less person. So if you went from 800, we got 50. We went to 825, we have 49. 850 is going to give us 48, and so on. So this is actually like a linear relationship. So that kind of tells us it forms like a line. We wrote increase wrong, but whatever. So we also know that maintenance costs $50 a month, and for each occupied unit. So we want to know what is the rent that maximizes profits. So this one's going to be kind of weird, considering it has a lot of variables and it's not, so clear. But the first thing we want to do is 50 units. So we want to call the unit something. We want to say we want to find out what the cost is. We want to figure out a good price for rent. So, let's just say, So I'll kind of go over with you guys what I did. This one I'll go into more detail as well. I'll use a different color. So the first thing we want to do is, find the cost of rent per month. So this is the thing that we want to find. What is the rent that maximizes the profits? So that's the C we want to find. And we let R just equal the number of units rented. So again, we want to, the fact is that we want to find the rent that, maximizes that. Or, maximizes profits. And the profits kind of depend on how many units are actually being rented. So we just let the number be R. And one of the things is that, what this relationship tells us is that as we increase rent by $25 a month, we get one fewer unit is rented. So basically it just kind of corresponds to a slope. And and one last thing is we're going to call the profits just P for profit, keep it simple. And now this is kind of where, again, where we have to use the information given to us. So we know that when, our cost is equal to 800, we know that our, number of units being rented is equal to 50. So we know every time you get a 25 increase in the cost, it gives us one less R. So one less unit is being rented. So that basically kind of tells us it's a slope. Or if you want, there's many different ways, but this is basically the equation that we get. I wrote it kind of funky. Maybe the better way to say it would be R is equal to negative 1 over 25, because that's basically our slope, or the 25 increase gives us someone less than R. Because remember that 25 is actually going to be your our x value in some case, because really you're trying to write R as a function of C. So 25 would be our x, r would be the would be the change in like y. So remember, it's like the change in y divided by the change in x. So we got a 25 increase. So as we move 25 up, we get a -1 increase. Well, -1, or we get 1 less r. So that's what we get. So we get our slope is equal to that. This is kind of like point slope formula, whatever you want to say, the y-intercept formula. There's many different ways you can construct this. But basically, this is what we get is that, when we plug in 8 is equal to, whenever the cost is equal to 100, we want r equal to 50, so kind of balances out. Again, there's many different ways you could form that equation. You could do, the equation of a line passing through 2 points, which would be h25, 49. Or you could use the fact that, this is equal to your slope, and then you use point slope. Now our profits are going to be, also an equation that we need to find. So our profits are going to be equal to r times c minus 50r. So remember that r is going to be the number of units rented, c is going to be the cost. So the profits is just going to be, how much they cost times the number available, because that's how much we're going to get. You sell 5 dogs that are worth $10 a piece, you get $50. That's a weird analogy, but whatever. And this 50 right here, this corresponds to, the maintenance cost. So it's $50 a month. It's just 50, not 150. So it's $50 a month, and we get R. So, again, the maintenance is per unit. So this is our equation for our profits. P is equal to R times C. So the total profit that we get minus the cost is going to be our, I guess you could say revenue if you like, it doesn't really matter. So I simplified this equation right here, and I just distributed that -1 over 25 and simplified. I got negative C divided by 25 plus 800 divided by 25 plus 50. What eventually I got was just 82 minus C divided by 25. So I wrote that in a simple form. That way, whenever I plug it back in, it would be pretty easy. Because this is what we want to minimize. Well, maximize. So we want to maximize the profits. It has 2 variables in it, R and C. Here we have R defined as a function of C. So, R is equal to f of C for some, but that's going to be our function. So when we take the profits, instead of talking about an R, because we know it depends on cost, we could just put in, our function. We could put in C minus 800 times -1 over 25 plus 50. So that's why I simplified it. R is equal to 82 minus C divided by 25. And, we had P is equal to R times 50 minus times R. So what I did was just plug it in right there into the profit equation that we have. And then what I did there is just simplified. You just, plugged in chug, distributed to C, because typically whenever you want to take derivatives, you always want to simplify as much as possible. So that's what it did. So P is equal to 82C minus C squared divided by 25, minus 50 times 82 plus, C divided by 25 times 50, that's going to be times 2. Well, this will just be 2. Move that over here to get the 84. It doesn't matter. It's just algebra, really. So what I got was the profit is going to equal to 84C minus C squared divided by 25 minus 50 times 82. I just left it as that because, that's just a number. It doesn't really matter what that is. I didn't need to actually calculate what the number is. Because what we need is the maximum. Well, we needed the cost to maximize this profit, so we don't necessarily need to know the profit value. So we take a derivative, we get P prime is equal to 84 minus 2C divided by 25, because taking the derivative with respect to cost. So we want to find the critical numbers. So critical numbers, whenever it's going to equal to 0. So we set P prime equal to 0, we get 2C divided by 25 is equal to 84. So, we solve for C, divide by 2, multiply by 25, and get C is equal to 1050. And we still need to verify if it's a max or min. I'll make it really easy. P double prime will be equal to actually no, that's not correct. Yes. So I'm kind of lazy when I wrote this out. I actually didn't find the maximum, which I'll do in just a second. I actually use the fact that P right here is going to be a parabola, and it's the value on the quadratic term is negative. So really it's just going to be a downward facing parabola. Downward facing parabolas have a maximum and it's finite. So I just use the fact that the vertex, or like the critical point of a parabola is going to be its maximum. Of a downwards facing parabola is a maximum. And then whenever rent is equal to that, I actually just plugged it in. I think that's correct. 150 a month. But really it's just that C equals 250 maximizes our profits. So this would be like, per month. And just to be clear on why the derivative is going to be, why it's a maximum, let's just do some quick interval testing. So 0, we'll do 1050. And let's, all right, let's do... All right, okay, we're actually doing an 80. All right, so P prime, we found the 0 that's going to be at 1050. We can actually plug in 0 because it's to the left of it. We don't actually care what, even though we do care about 0, but the fact is that this is linear. This just looks like a line. So if we plug in 0, we plug in 1, it doesn't matter which value you plug in, but we get negative here. Actually, no, we get positive here. So we get 84 times a small number. 84 minus C times a small number. It could be like, 1/2 if you wanted. It doesn't matter what you want to call it, but it wouldn't be too hard to verify that you get in the first interval, you get positive. From 0 to 150, you get positive. From 150 onwards, you get negative. So this would be like P prime less than 0, P prime greater than 0. This isn't really too hard to verify. And I feel like this is not the hard part of the problem anyways. But, you solve for C, you get the C is equal to 1050. And, that's the cost. So basically what that tells us is that, the profit's going to be maximized when we set rent at $1,050 a month, which also corresponds to like $40,000 a month. I just kind of did that for fun. These problems themselves aren't too bad. You just have to go through these sections carefully and try to understand the equation and try to understand the setup. Like this one itself was a bit annoying. It took me a second to figure it out, but I was really just like, okay, manager of apartment, 50 units. What does that mean? And what you kind of have to understand is like, okay, when you set rent to equal $800 a month, all units are rented. So that basically tells us is that rent, rent will be our independent variable, and the units rented is going to be that dependent variable. So that's a relationship right there. And what this tells us, as you increase rent by $25 a month, one fewer unit is rented. That basically gives us a way to form our relationship between, rent and cost. And we know that you have maintenance costs of $50 a month for each occupied unit. That itself is just kind of a side thing. You don't really need to account for that. I mean, it doesn't really play a huge role. But, you want to maximize profits, and then you have to understand how profits are calculated. So you take the total revenue and you subtract, the cost. So that's how you get the profits. But I hope this was helpful. I know it's kind of tricky at first and it's weird, especially at the setup. But just make sure to draw a diagram when you can, and try to understand. You're trying to be more general. You're trying to abstract things. Like here we had just two numbers, A, B. We want to find just two numbers, A, B. but the product is equal to 192, and we wanted to minimize that expression. And the goal was that they were the minimum value for those expressions. So when we needed to talk about them more generally, when we said, okay, in this case, we're going to let, all possible numbers. So all possible numbers such that, their product is equal to 192. And whenever we consider all possible numbers, this is how we get this relationship right here. And then the minimum value of f, that b value, that in itself was our minimum. So you have to kind of be careful sometimes about, especially with the number problems when you do more abstract or the applicable problems, the more applied problems, is that you have to understand that a lot of these problems or optimization problems are working in this thing we call parameter space. You just want to know if you change this thing, if you change, the length of a box, you change the strength of something, you want to change how something, you want to know how something changes and how something else will respond to that, then you need to use derivatives, you need to use all that kind of stuff. But thank you guys for watching. I hope this helps. I understand this section is kind of confusing and kind of hard at first, but you guys are pretty smart. You guys can do this. I believe in you guys. But adios. Peace out.